colleagues, I'm delighted to introduce our guest speaker, Professor Richard Thompson. So, every year now we have a special lecture which coincides with the annual general meeting, which we'll hold later on this afternoon. So the purpose of this lecture is actually just get some people here to the general meeting. Not quite, but Richard is an Associate Dean of Research at the university, and he's a Professor of Marine Biology. He specialises in the ecology of shallow water habitats. He got his first degree from Newcastle upon Tyne and a PhD from Liverpool. And over the last decade, as I'm sure most of you are aware, he's focused his research on marine debris and has published a lot on this topic. In 2004, his team reported on the presence of microplastics in the environment, and that was published in the journal Science. His subsequent research examined the extent to which microplastics were retained upon ingestion and the potential for microplastics to transport pollutants into organisms. He's a lead guest editor for a 200-page volume in the journal Philosophical Transactions of the Royal Society, focusing on plastics in the environment and human health. He's a co-author of the European Union Marine Strategy Framework Directive text on marine litter, and has recently prepared several reports on this topic. He's known in the highest circles, I'm informed, as the godfather of microplastics. He also sits on several international committees, including the UN Advisory Body on Marine Plastics and the Expert Group on Marine Debris for the Marine Strategy Framework Directive. I think it's true to say that not many people really can stimulate a whole new topical research field, but I think it's really fair to say that Richard has done this, and that field has continued to expand exponentially. So I'm very interested to hear what you have to say about it.
Thank you, Colin. I think that's more than generous. I would say thank you very much indeed. And it is an absolute pleasure to be here at the MBA. My association with the MBA goes back to the days when I was a student, and my then PhD supervisor persuaded me of the benefits of joining the Marine Biological Association. That supervisor was Steve Hawkins, who went on to become MBA director in the future. So you may have said that he was helping to sort of ensure his salary as the generations of students went through, but I'm really grateful to Steve for introducing me to the MBA. Indeed, I worked for the MBA here for a while when I was in that difficult position between postdocs and getting my first permanent position. So I've been very grateful to the MBA over time and the collaborations that I've had, and those are still ongoing since I've moved to Plymouth and working at the university. We've had extensive collaborations with members of the staff here, we've had shared PhD students here, and I hope that that continues long into the future. So thank you very much for inviting me. I understand that I'm actually second in line, that you were originally going to get a talk on oil from, indeed, Professor Hawkins, who was my PhD supervisor. We've switched to plastic, derived from carbon, from oil sources, so it's related, and I will try and touch on oil somewhere in the talk if I can.
I saw last year.
It's last year. So, marine debris. Of course, if you go back to the first slide, you look at our planet from a distance. It looks fairly blue, but as we start to zoom in on the surface of the oceans, we realise that actually it's speckled with small bits of a variety of colours that are not natural in origin. We find marine litter, marine debris distributed throughout the ocean surface, literally worldwide. Some places quite high concentrations, others relatively low. We also find marine debris, predominantly plastic, right down at the bottom of the deep ocean, thousands of metres beneath the sea surface. That's maybe surprising, since much of this debris, when it enters the ocean, is buoyant. But over time, because of accumulation of fouling, even buoyant items of plastic can sink down towards the seabed. And here we see the seabed of the Mediterranean. I guess for many of us, where we're most likely to encounter marine debris is on shorelines. And it's difficult to walk on a shoreline anywhere in the world these days without, in the space of a minute or so, even less in many places, encountering marine debris, like this single-use plastic bottle here in Slovenia. I've already used the word plastic quite a lot. Now, the title of my talk is about marine debris. A lot of what I'm going to speak on, however, is plastic. And I want to explain why that is now. And largely because most of the marine debris we find is plastic. This is data from OSPAR, varies from place to place, but typically 70–75% of all the litter that we find is plastic, accompanied by smaller quantities of metal, glass, and paper. But the majority is plastic. And so when we're thinking about the issue of marine debris, when we're thinking about solutions to the problem, I think it's reasonable to focus, this is a starting point, on plastics. Now, if we think of plastics and plastics debris, that can span a whole range, orders of magnitude of size. People tend to talk about marine debris, they talk about plastic as though it's one homogeneous thing, but actually it's a very, very heterogeneous mixture of large items of mega debris, like this, the tail cone of the Ariane space rocket, I think the European Space Agency funded. Not all plastic, but it's got plastic composites in it, it's washed ashore here on a shoreline in the tropics, right down to some of the smallest pieces of plastic, and these are bits of microplastic. Actually, these are towards the large end of the microplastic fraction. These are bits a couple of millimetres in size from the River Tamar, close to us. And if we look in the River Tamar, we'll find by numerical abundance that these microplastics now far outnumber the larger items of plastic debris. And microplastics can go all the way down to the limit of detection, around about 10 to 20 microns in size. We suspect there are smaller pieces out there, but they're below the levels that we can currently detect in the environment. So we've got a category of contaminant that's spreading on size classes over orders of magnitude. We've also got a category of contaminant that is present in many different shapes, that's present in a whole variety of different polymers that have a wide range of different interactions with the environment and with the organisms that live within it. Different buoyancies, different chemical compositions. So it's very difficult to make any generalisation about the environmental effects of plastic, or even about the solutions, because it's a very heterogeneous mixture. We already know, for the larger items of plastic, that these present considerable economic consequences. Draining away resource from areas where, arguably, taxpayers' money might be better spent. The US West Coast alone, it's estimated that $500 million every year spent on clean-up costs. If we look at many of the European member states, we see figures into the millions of euro every year spent on cleaning up coastlines just to keep them attractive for tourism, to keep ports and harbours operational. That's considerable expenditure. It's only part of the total financial picture, I'd argue, but it's a clear indication of how important it is to keep our marine environment clean. We're also starting to see effects on human well-being. This is a study we did with a PhD student jointly with psychology at the university, where we looked, it was one of her chapters, a student called Kaylee Wiles, we looked at the effect of small quantities of litter on what the psychologists might call the restorative value of a trip to the seaside. The fact we all want to go to visit the sea and it makes us feel good. Well, how is that feel-good factor altered by the presence of litter? So what we did in this study, these were randomised photos presented to an audience. This is just a selection of them, but we had a range of beaches around the southwest of the country. We had some that were completely devoid of any debris at all, some that had natural debris, seaweeds strewn on the strand line, and some that had litter. And these yellow boxes, I stress, weren't around the litter in the study. I put them there just to highlight that this wasn't a massive midden of litter that you might find at the end of a day's beach cleaning activity. These are fairly discrete quantities smattered about in the photo that at first glance you probably would miss, which is why I've put those yellow boxes around them. And we found significant depression of this restorative value of the trip to the seaside by the presence of litter. And interestingly, because we had two categories of litter, we had fishing and shipping related debris, and we had single-use items of packaging. And the single-use items of packaging had the greatest sort of negative effect, depressing people's feeling, their mood going to the seaside. We weren't able to disentangle the cause of that. One could argue that it might be because maybe to some extent, although of course we don't want to see fishing-related debris in the oceans, there is some explanation behind it that some gear is going to be lost in storms, accidentally, whereas the packaging-related debris is kind of completely avoidable. So we certainly saw this negative effect on human well-being, if you like, from the point of the restorative value of trips to the coastline, at what I would argue are pretty low densities of litter, something very typical for any shoreline that we might visit. We know also that marine debris, the larger items, presents a considerable hazard to mariners, resulting in hundreds of unnecessary call-outs for Coast Guard, lifeboat agencies every year, and of course economic losses to shipping, lost time, and potentially quite serious hazards if vessels might run aground as a consequence of entanglement. I guess most emotive and most widely reported in the media are the encounters with wildlife. And a few years ago we were asked to document these for the Convention on Biological Diversity. We found over 300 scientific papers at the time that documented encounters between wildlife and marine debris. Around 700 species. 13% of those species were already considered threatened in terms of their IUCN status. Now that's not to say they were threatened by the marine debris. It's almost impossible to isolate out the single reason that means that a species might be considered threatened. But I think it's fair to say that the additional challenge that litter presents is certainly not going to be advantageous to those species that are already threatened. And a further justification, if it's needed, for why I consider plastics as being a major focus when we want to improve the status in terms of marine debris, is when we break down all of those reports by material type, we see that 76% of all the encounters, if we look at it by species, are with plastic, and if we look at it by individual, over 90% of all the encounters are encounters with plastic debris. So there's a lot of plastic debris in the environment, and it's resulting in a lot of encounters with wildlife, some of which we know to be potentially harmful. We know, for example, that seabirds are harmed as a consequence of entanglement in marine debris. There's also a good number of seabirds that ingest marine debris. The extent to which ingestion of marine debris causes harm is less clearly established, but in some seabirds, for example the northern fulmar, 95% of the population have got plastic in their guts. It's 95% of the birds flying over the North Sea have got plastic in their guts. And the key researcher Jan van Franeker from the Netherlands, who's working on this for many decades now, estimates that there are literally tons of end-of-life plastic circling above the North Sea in the guts of birds as we speak. The quantities are quite considerable. If we scaled them up to the volume in a human, you could be talking anything in the region of a kind of coffee cup sized volume in your guts just now. So the quantities could be quite considerable. And it's difficult to imagine how that can have a positive effect. Isolating the single harmful effect, isolating the effect of plastic, is a very, very challenging thing to do, particularly with a seabird. But suffice to say, we're seeing this incidence of encounter at a population level, and the quantities are quite considerable. Establishing how much that affects the birds is a difficult one. We also know that ingestion of plastic is widespread amongst commercially important species. We published a paper jointly with the NBA a few years ago where we used fish taken in some of your standard hauls. We looked at over 500 of them, and in around about 2/3 of them we found small quantities of microplastic. Only 1 or 2 pieces per fish. This is not a story about a threat to human health from the point of view of eating seafood or shellfish or fish, because the quantities are quite low. But it's clear that the incidence of encounter in natural populations is now quite considerable, and that applies to both fish and to shellfish. And about 10% of the published reports that we looked at when we did that study for the Convention on Biological Diversity related to encounters with microplastics, these really small pieces of plastic. And I want to turn to microplastics a little bit now for some of the rest of the talk, and then I'll broaden it back out again, because the term microplastics really came into being from work done in Plymouth, jointly with Sir Alistair Hardy Foundation for Ocean Science. We published this paper in 2004 called Lost at Sea, Where is all the plastic? And the reason for that title was because if you look at time series data of marine litter, you'd imagine you would see an exponentially increasing trend that matched production statistics, which incidentally have gone from 5 million tonnes of plastic produced in 1950 to 300 million tonnes of plastic produced today. But if you look at data for accumulation of litter in the environment, it's now found in many more environments, we think, than it was found in 1950, but that's difficult to separate because there's a lot more people studying it. But if you look at time series, we don't have that many, they tend to just go like this, up and down, lots of noise. What was the explanation of that? Why don't we see this trend? And one of the things that we explored was, is it that the plastics, although not degradable, have actually fragmented into many, many small pieces over time, and those pieces are sufficiently small that they're not recorded in routine monitoring. And so we went back, using the time series from the CPR, we went back and we showed that there had indeed been an increase in the abundance of microplastic pieces over the 40 years of study that we considered. So that, to some extent, explained, if you like, where some of the missing plastic might be. It certainly doesn't explain all of it, and people have gone on to try and model that and understand it. And we still know there's a lot of debris missing somewhere, and we don't fully understand where it is. But that was the gist of this paper. These are publications on the topic with the keyword microplastic in it since 2004. So you see that these are scientific papers in peer-reviewed literature. The topic has really kind of taken off quite considerably, and there are groups literally all over the world working on microplastic now. Some of the work that we've done in Plymouth has demonstrated the potential for physical harm associated with ingestion of microplastic. Small quantities, even 1% of plastic mixed in marine sediments, can affect the ability of sediment-dwelling invertebrates to gain energy from food, to process their food and to gain energy from it. Which is, of course, going to have knock-on consequences for their growth, their reproductive output, and indeed potentially for the predators that rely on food. There's also, maybe more widely documented in the media, concern about the chemical challenge that plastics might present. If you're a marine organism and you ingest plastic, does it have the ability to transfer chemicals to you? And that's one of the things that we've been studying for a number of years now. And this data looks a bit complicated, but what we're looking at here is pairings of different plastics with different contaminants that are already in the environment. So if I explain, there's two routes by which chemicals might be transferred by plastic. The first one, which is covered by this slide, is we know that when plastics are in seawater, they will attract very, very rapidly hydrophobic contaminants. Man-made chemicals that are already in the environment, that are hydrophobic in nature, will latch onto the surface of the plastic very readily because they're hydrophobic. They'd rather be on a hard surface than free in the water column. And in a matter of days, you can get concentrations of some of those chemicals to orders of magnitude greater than they were in the surrounding seawater. So we've almost got the opposite here of what my marine pollution professor used to teach me in Newcastle, which was the solution to pollution is dilution. Here we've got this dilute going to a concentration again. So what's the potential if that concentrated package is eaten by a creature? Can those chemicals come off again? One of the things we've been exploring. So these are combinations of plastic and persistent organic pollutants that are present in the environment, phenanthrene, DDT, DEHP, with both polyethylene and PVC. And what we did was we put the clean polymer, clean piece of plastic, into what was effectively a natural concentration of the contaminants that you'd find. Natural is not quite the right word. An environmentally relevant concentration of those contaminants. We put the plastic in, it absorbed those chemicals onto it in the same way that I've already described. We then moved the plastic, the contaminated plastic, to clean conditions. And we moved it to 3 different types of clean conditions. Back to clean seawater, to the guts of a cold-blooded marine invertebrate, and to the guts of a warm-blooded marine invertebrate. And these were in vitro studies. It was studies done with conditions, chemical conditions in the solution, mimicking those in marine organisms, warm, cold-blooded, not actually to living animals. What we see, because this is a reversible equilibrium, is that if you move the contaminated particle to clean conditions, the chemical starts to come off. It comes off even in cleaner seawater. But as you move to gut conditions, particularly those of warm-blooded organisms, you see an increase in the rate of delivery of that chemical from the plastic, up to 30 times greater than the release into seawater on its own. So there's a mechanism here for the delivery of chemicals via plastic to organisms that eat it. But note that this is dealing with the rate. It's not dealing with the total dose delivered. And we also have to keep in mind that an organism in a contaminated seawater is exposed to those chemicals via a range of other routes other than the plastic. If it's respiring by taking water over its gills, that water will be contaminated with the same chemicals. If it's eating food, which has already acquired a burden of those chemicals, that food will present a route to the organism for chemical transport. So the key thing really has been to establish the additional contribution of the plastic in terms of chemical transfer. It's clear that plastics can acquire chemicals, it's clear that they can deliver them to organisms upon ingestion, but to what extent is that important from an environmental pathway? Well, our current work suggests that probably it's relatively minor, it's relatively trivial compared to all of the other sources. But it's difficult to give any single answer to that because we've got a wide range of different creatures that feed in different ways, that have got different pathways. Some of them are taking their oxygen over gills from the water. Other creatures that are ingesting marine litter, like the seabird, not exposed so much by the direct route of living in water at all, but it's still ingesting the debris. So the pathways, the extent and relative importance of those pathways is going to vary according to where it is you live and how you feed. But the current evidence suggests that probably, for most organisms, the transfer of chemicals from seawater via plastic to an organism is likely to be relatively trivial, the extra role of plastic. What is needed, however, is more work to look at chemical additives, chemicals that are incorporated at the time of manufacture, for good reason, as flame retardants, as plasticizers, as antimicrobials. These can be present at the time of manufacture in concentrations that are considerably higher than any concentration you'd reach by absorption. What we need is more work actually to look at the potential release of chemical additives. But a key question there is to what extent will those chemical additives already have left the plastic, have migrated out of the plastic, by the time the plastic object gets into the sea in a size that's small enough to be readily digested by a range of marine creatures. It could be all of those chemicals of concern have already left the plastic. So there's quite a lot of work to do relating to the degradation, the release of those chemicals, in order to understand, again, whether or not plastics present an important pathway for chemical transfer, for chemical additives. We know that from work done here and elsewhere, this is one of the early studies that we did, that microplastics are now distributed throughout the world in terms of intertidal marine sediments. We also know that they're widely distributed in the deep sea, and this is work that we did jointly with colleagues in Barcelona and the Natural History Museum. And interestingly to me was that in some of these samples from the deep sea, we were finding a greater abundance per unit volume of sediment, and there's a difference in methodology here that we need to keep in mind. But if we compared a cupful of sediment from the deep sea, that volume of sediment would contain more microplastic than a cupful of seawater taken from the surface of some of the oceanic gyres that we hear so much about. So the concentrations in some areas of the deep sea are now really quite considerable. And maybe this is the ultimate destination for all of that plastic, despite it being buoyant at first entry to the sea for many polymers. It's sinking perhaps down to the seabed. But there's very little extra data beyond this for the deep sea at the moment. So we still don't have any real clear idea of spatial patterns. And this data has been taken by others, by modellers such as Eric Van Seville, who have built up patterns of where they predict. And this is a prediction. It's not a reality. It's based on the empirical data, but it's predictions of where you'd expect the hotspots of microplastic distribution at the sea surface. Now, it's important to recognise that these are persistent, cumulative contaminants. They're not degrading at any rapid rate in the environment. And so, if we look forward, what's the concentration going to be like in the future unless we do something about it? As part of an NC's working group in the US, this is one of the things that we looked at. And a key paper by Jenna Jambek came out in 2015, where Jenna tried to estimate on the basis of plastic production and waste disposal what the likely escape was to the marine environment. And she came up with low, medium and high scenarios. But in short, we could be looking at 3 times as much plastic in the oceans by 2025 as there was in 2015 when the study came out. So unless we do something about it, it's clear we've got a problem that's only going to grow, because these are very persistent, long-lived contaminants. And just to set this into some kind of comparison, I said I'd try and bring oil in, and I probably should have changed this to a Torrey Canyon slide, but if we think of the deep water horizon, we had a very acute, localised input of essentially fairly biodegradable hydrocarbons. Somebody made the point to me over lunch that the oil from the Torrey Canyon spill is long gone now. It was very serious at the time, but it is relatively biodegradable compared to conventional polymers. 0.7 million tonnes of fairly biodegradable hydrocarbon And then, if we use Jenner's figures for the inputs of plastic debris, what we see is that plastic is not acute and it's not localised. It's a chronic, very diffuse contamination of up to 17 million tonnes per annum. And it's relatively non-biodegradable. So it's sort of, I'm not trying to say that I think the plastic is necessarily more harmful than the oil. What I am trying to say is that the quantities in terms of the amount of carbon is very substantial, but it's less easy to see because it's spread far and wide. And it also means that when policymakers ask for evidence of the harm that plastics might cause, it's quite challenging to obtain that. It's relatively easy, and it saddens my heart to see the consequences, but to get information on what it was like before and after an oil spill, and to demonstrate effect, and to take that back to industry and place legal charge for compensation on fisheries, or loss of wildlife, or loss of habitats, is a relatively easy thing to do where you've got a substantial input in one place and one time. Where you've got diffuse inputs right across the globe, it's going to be almost impossible to isolate the harmful effects of plastic on populations, on species, at that kind of level, because we're dealing with a widespread veneer, really, across the planet. And in a way, it's akin to what we might think of in terms of biological impacts from pulse versus press kinds of disturbance. We tend to think about these press disturbances as particularly relevant to long-term, wide-scale anthropogenic disturbances, such as removal of fish stocks in a fishery. And that was demonstrated, for example, in the intertidal work by Juan Carlos Castilla, where he looked at exploitation of mollusks. It's very difficult to see because it's so far and wide compared to these kind of pulse disturbances. So enough about the problem. I said, are there any solutions? And I kind of want to turn to that for a moment. But even as I talk about solutions, you'll see me talk a little bit more broadly about the underlying causes of the problem. Because we tend to think of this, as the title of this talk, as an issue of marine litter. But actually what I would argue is that marine litter is a symptom of the problem. It certainly isn't the cause. And if we want to get to the cause in order to achieve progress, then we need to look to the underlying causes of the problem. The point that I really want to make here is that this is a very different kind of environmental problem to many of the challenges that society faces at the moment. If we think about sustainable exploitation of the fishery, which kind of harks back to the origins of the MBA, if you like, we can try and fish sustainably, but however we fish, the immediate consequence is that there's less fish in the sea. There's a direct link between the thing that us humans want and the consequence for the environment. And it's exactly the same if we all want to live by the coastline. There's immediately less habitat available for creatures to live in. But that's slightly different when we start to think about plastics. Because if you think of the many, many benefits that plastics bring, and I want to be absolutely clear about this, that the plastics are not the enemy in this story. Plastics have the potential to reduce our footprint on the planet. It's not the plastic that's the problem, it's what we choose to do with it. But if, for a moment, we think about the things we do with plastic, whether that's lightweight parts in cars and aeroplanes that will help to reduce fuel usage and carbon emissions, whether it's protective gear for this fisherman or the nets to catch the fish, or whether it's packaging that will help extend the life of food and drink on shelves in our shops and so reduce wastefulness of food. It'll help to reduce food waste. And any of the other things, those of us that might have a plastic body part on us, or think of all of the uses in education, the computer screens, all of this kit that would not have been available to us if we were still packing things in boxes made of wood and metal. This computer would be much more expensive than it is today. So plastics are not the enemy here. If you think about these things, to go back for a minute to think about my housing and my fisheries example, there's nothing in these benefits that requires an emission of debris to the environment. The societal benefit is completely decoupled from the environmental problem. So in theory, at least, it should be possible for us to retain all of these benefits without the negative consequences, in theory. It's not about us all having to go around with the light switch turned off, or us taking less long-haul aeroplane flights. It's about us doing with this material differently. And I realise now I've left something in the bag which is over here, which I just want to dig out. So this is a book, actually. This is the second edition, but the first edition was published in the 1930s, and it's a description of plastics from the 1930s and 1940s and what the future of what we would call our plastic age might bring. So it's very much looking forward, nearly 80 odd years ago now. And it's a book that I found on my grandfather's shelf, actually, after he passed away, and I thought, well, that looks like an interesting read. It was before I ever started to work on the topic, but I just thought it looked quite interesting to see this perspective of a material that's really quite new to us. And the whole book is set in the context of an imaginary plastic man, okay? And it talks about the plastic man's life, and I mean the whole book, so I'll just give you a little extract. But this imaginary plastic man will come into a world of colour and bright and shining surfaces, where childish hands find nothing to break, no sharp edges or corners to cut or graze, no crevices to harbour dirt or germs. The walls of his nursery, his bath, all of his toys, his cot, the moulded light perambulator in which he takes the air, the teething ring he bites, the unbreakable bottle from which he feeds, all plastic. As he grows, he cleans his teeth and brushes his hair with plastic brushes, clothes himself in plastic clothes, writes his first lesson with a plastic pen, and does his lessons in a book bound with plastic. The windows of his school, curtained with plastic cloth, entirely grease and dirt-proof. The frames, like those of his house, the window frames like those of his house, moulded plastic, light and easy to open, and never requiring any paint. It goes on, plastic man, ages and ages, until he wears a denture with silent plastic teeth, and spectacles with plastic lenses, until at last he sinks into his grave in a hygienically enclosed plastic coffin. now, many of those things have been borne true, but one of the things that's really missing from this book, when it was anticipating the benefits that these wonderful materials could bring, was the accumulation of litter. So where is it that we've gone wrong? Where have we gone astray? Right. Incidentally, this is me, 50 years ago, clearly a child of that plastic age, surrounded happily at Christmas, and actually, I've still got Plastic Sailor, and he's still functioning very strongly. He makes some appearances at talks with me, but he's getting a little older, and I don't take him everywhere. But I'm clearly one of the products of this plastic age. What have we done? Where have we gone wrong? 40% of all of the plastic we produce, and we're making 300 million tonnes of plastic items every year, 40% is used for single-use items. Things that are used once and then disposed of, typically within less than a year. And yet, if you think about the benefits of plastics, one of the main things, apart from them being inexpensive and lightweight, is their durability. And what we've done is not focused on those long-term applications that are highlighted back in the 30s and 40s, but we're focusing most of our production on single-use applications. And we're using 8% of world oil production to do so. And if we've got such a rapid linear use of non-renewable carbon via short-lived applications in single-use plastics, it's hardly surprising that we've got a colossal waste management problem as a consequence. So the underlying cause of the problem, in my view, of which marine litter is a symptom, is this rapid linear use of resource and conversion of it from relatively degradable oil into a form that is much, much harder to be degraded by biodegradation. This is the centrefold from Time Life magazine in the 1960s, extolling the virtues for the children born into that plastic age of this throwaway society, how it was going to make life so much easier for us because there'll be so much convenience plastic around. And of course, now we're beginning to realise that there is only the one planet and there is literally no way for all of this stuff. It is accumulating in waste management. Well, this is an unmanaged system in Albania, but it's also accumulating in waste management systems in landfill or requiring incineration. And the majority of that waste is plastic. If we look at data from beach surveys from Marine Conservation Society or Global Conservancy, we find that about 50% of what's picked up on our beaches is single-use items or fragments thereof. So we're producing a lot of single-use items, used very rapidly, and it's those items that are particularly pervasive, particularly common when we look at the categories of litter on beaches. Sure, it varies from place to place. In some places it's going to be fishing related. If we go to some parts of Europe, it's cigarette butts, but there's an underlying trend there of single-use items. So what can we do about the problem? The things that have been discussed fall into really three kind of categories. You know, our natural tendency, I think, when we see a mess, is to want to try and clean it up. And there are numerous approaches to do this, to try and clean the ocean. But my concern now here is that if we're not careful, we distract attention away from what should be core business. When you consider that we've got substantial quantities of plastic accumulating in the deep sea, we've got plastic in the guts of organisms, plastic embedded in coral reefs, how is it going to be possible to solve this problem by clean-up? And even if it were, that would mean that we would be cleaning up our planet in perpetuity. The thing to do is to stop this plastic going into the ocean and to focus on stopping it getting in. And that's nothing against the work at Marine Conservation Society. I'm a member of such, and I've helped in many beach cleans. But we don't want to be cleaning beaches forever. There are far more important things we could do with our marine conservation focus than cleaning up problems that could be avoided. We could think about starting to plug some of the holes, and there are many of them, and that's illustrated by this colander. But the danger is what happens is the flow just comes and escapes somewhere else. What we really need to do is to redirect the flow right up at the top, and that's a sample of beach litter collected, and it kind of illustrates the single-use nature of these plastics. And as I've said already, most of this is derived from non-renewable oil and gas in the first place. And actually, plastics are inherently fairly recyclable. So one of the solutions to this problem, which is a kind of double benefit really, is to take our end-of-life plastic and to recycle more and more of it. Because ton per ton, that will reduce the amount of waste that we generate, whether that's going to landfill or whether it's escaping as litter to the environment. If it's captured, there's the potential for escape, or the need to deal with it in a managed system is taken away. And actually, it will also reduce our reliance on non-renewable oil and gas as a source, as a linear source for fueling this kind of throwaway culture. So that's the direction we need to go in. And actually, most plastics are inherently recyclable. What prevents us recycling many of them is an inadequate design that doesn't consider end of life at the design stage. So to me, that's what we need to be doing more of. And it has a lot of synergies with waste management on land. It will also help to reduce the amount of waste we're generating in managed systems. Here's an example of where inadequate design is hindering our ability to capture end-of-life plastics. These bottles are all made of the same polymer. They're all made of PET. This is our most recyclable polymer. They're all plastic drinks bottles. They're not difficult things to collect, like a microbead from a cosmetic. They're all readily available for collection. And they are widely collected. But if I talk to a recycler, they'll tell me that they want this one, the clear one. They're not interested in the orange or the blue one, because the presence of that pigment can reduce the value of their recyclate by up to 80%. And at times when the price of fresh crude oil is very low, that makes it almost impossible to recycle these. Despite the fact that they're made of the same polymer, they have the same logo, the same information on the bottom, the little triangle that says recyclable. But keep in mind, recyclable is a theory. It doesn't mean it's economically viable. The presence of the pigment is doing nothing to protect the goods. It's not extending the shelf life. It's nothing to do with getting goods safely to the consumers. It's to do with marketing. And I have nothing against the marketing of these brands. Of course, that's important to the manufacturers. But if that marketing is cutting against our ability to recycle one of our most recyclable polymers, surely that's an example, a blatant example of inappropriate, a lack of consideration at the design stage for the fate at the end of life. Because one of the reasons that we have a lower engagement, if you like, with the recycling is that people don't necessarily believe it. And it's hardly surprising when you see this in one of our most recyclable polymers. There are also what I would consider some conflicting drivers in here. We're seeing increasingly the use of bioplastics to make plastic objects. Now, let's be clear what a bioplastic is. It's nothing about the biodegradability of the plastic. What it refers to is the carbon source. It's referring to a natural carbon source from plant material rather than a natural source from fossil derived carbon. So in that sense, it's sustainable because of course we can grow new plants. But having a biosourced plastic does nothing at all to reduce the quantity of waste we produce. It does nothing at all to reduce the quantities of litter that we might find in the ocean. Do we really have sufficient land on the planet to be growing crops, to turn them into plastic, to throw away? Isn't the renewable source of carbon the waste that we're already generating if it was better designed? So to me, this is a distraction of the problem. But if you look at it from a currency of carbon, you could consider that it was sustainably the right thing to do. But if you look at the whole picture, you realise actually there's a much better source of carbon. It's that end-of-life plastic. But what we've got to do to be sure that we can capture that is make sure that we're designing products with end-of-life in mind. There's also the myth that biodegradability can solve the problem. And there's lots of products out there that are labelled biodegradable. And in many cases they're marketed in such a way that I would argue suggests at least quite strongly to the consumer that that is a green choice. But if you look at the standards required to label something as biodegradable, what does that mean? It means that the product, if it's already been shredded into small pieces mechanically, will degrade in commercial composting conditions to some extent, not completely, over 180 days, but temperatures look up to 70 degrees Celsius, 50 to 60 degrees humidity, highly aerobic conditions, specific pH, conditions that are not met in many, and I'm interested here if you know of any, natural environments. So the biodegradability is not a solution to the problem of litter degrading in the environment. It relates to very specific conditions where you know and can understand and manage the waste stream in the conditions that you will find there. And what is happening to some extent is you're taking long-lasting products that can have a durable life and service for many years, and you're turning them into something that will disintegrate more rapidly, that will have a shorter shelf life. That's working against one of the main benefits of plastic. The last thing you want is food containers in the supermarket or in your pantry to be dropping apart into bits and causing all the food that's perished. I heard a story of animal feed in Asia being supplied in containers that I think actually could be fed to cattle and eaten. And somebody said, well, what do you do to protect those containers from the rodents? Well, we have to overwrap them in polythene. So, the main benefit of plastics is their durability. And anything you do to compromise that is really working against the benefit that they bring, when actually they could be recycled. But, heck, if you incorporate something that's going to make them fragment more quickly, to degrade not as a plastic but as an item. Sure, the carrier bag here, after 50 days, is degraded, but it's now degraded into millions of pieces. The last thing a recycler wants in their supply chain is any, even very small quantities of biodegradable plastic, because it will completely contaminate the batch of plastics that they're producing, such that it'll have to be wasted, because what they don't want to be doing is selling plastic that's got a short-lived application. So whilst there are some specific applications of biodegradables, they're certainly not centre stage in terms of any solution associated with marine litter. Some things I think, maybe we need to think about just doing without them altogether. Some of the work we did on microbeads in cosmetics showed that a single container can have 3 million particles in it. And I'm pleased, to see that there's been some interest, at least, in introducing legislation to tackle that, because really there's nothing here the consumer could do. You can't take these individual microbeads to be recycled. If you use those products, it's inevitable they're going to pass through wastewater treatment, or they're going to pass through your plug hole, some are going to escape wastewater treatment and end up in the environment. The quantities, I have to say, are relatively small compared to the whole scale of the problem. We're not going to solve the issue of plastics in the environment by banning microbeads. But what I would argue is it's a totally avoidable source. It's not clear to me what the societal benefit is at all of cleansing ourselves with millions of small pieces of plastic. It seems unnecessary and avoidable, and therefore appropriate to take action. But the scale of the difference that it will make is probably similar to single-use plastic carrier bags. So if we're really to make progress on this issue, we're going to need to look at a wider range of products in order to make sure that end-of-life plastics can actually be captured effectively in recycling. There's no single silver bullet we can wave. More recently, and again it's the same argument about designing products for life and for end-of-life, I would argue. This is release of fibre, plastic, synthetic fibre, from garments, actually bought quite locally to where we're sitting today, but I better not name the store. But 3 different types of polymer you see at the top. Now, the garments are fairly similar in terms of the way they look and the properties, But some of those garments, these are then what was emitted in terms of fibres when you take them home, you wash them. This is a standard domestic washing machine. We've got sort of 5 to 6 times as many fibres emitted per wash from some of these fabrics that we have from others. Now, why is that? Is that about inadequate design? It's not good for you as the consumer, surely, because what it means is your garment is falling apart 4 to 5 times more quickly than some of the others, and that's resulting in an emission to the environment. So again, there may be things that we can do at the design stage to help to reduce some of these emissions. Ultimately then, it's about designing things for life and end of life, but I think it's really going to require appropriate labelling and standards, and that needs to be driven by policy. Whether it's something as simple as a traffic light system, where you get a green dot on the product for minimum material used to do the job, easy to recycle, contains recycled content, and a red dot for the opposite end of the string. But we need something that's simple for people to understand and to interact with. Whether that's the supermarket chains or whether it's the individual consumers, we need a simple system that's fair. This table's far too difficult to see from the back, but I put it up and I'm nearly on the final slide for 2 reasons. And the main one really is to say that there's no single answer. It's got to be product by product, but by that I don't mean we're looking at millions of answers. It's a small suite. I'd say it's probably less than 20, but we need to think about things that are product specific. We also need to think about them geographically, because the way the solutions might or might not work varies from country to country, and that's why I put this up. This is from Gemma Jambek's study. It lists the top 20 worst anticipated polluters in terms of plastic to the marine environment. Now, the US is in there, and China's in there, but they're in there for very different reasons. China is there because it has a very relatively low standard of waste management, but its citizens produce fairly limited quantities of waste. They're quite frugal, they're not producing a lot of waste, but they're in the table because the waste management system's not so good. If we look at a country like the US, where the waste management infrastructure is much more developed, it still makes it into the table because its citizens generate considerably more waste per capita than is the case in China. And Europe wouldn't be out of the picture if it was considered as a European Union. Unfortunately, it's fallen off into many different countries, so it's hard to shake a stick at. But I don't think we're doing any better here than in the US. So in terms of contamination of the environment, it depends how much of this plastic you're using and how much is escaping. But it's about a waste management solution that's on land. So one of the key things we need to do is to take this passion for the marine environment and point it back onto the land, which is where the answers lie. And I reckon that if you'd heard I was going to give a talk about waste management, probably at least half of you wouldn't have come. But it's taking that passion and focusing it kind of where it's needed. So in my view, to summarise, I think that marine debris is a solution of an inefficient and outdated business model. And by that I mean this linear use of resource from oil to waste. It's not directly coupled to societal benefits, so it should be fixable fairly easily. It damages resources, whether that's economy, wildlife, ecosystem services. There's clear synergistic benefits, particularly in terms of resource efficiency and waste reduction, that can be achieved, in my view, by a greater emphasis on product design. We have to recognise that while there are solutions, there isn't a single solution. It's not a paper or plastic debate. There is no single answer to this. But in terms of traction towards solutions, I think one of the things that we really do have working in our favour here is that it's a highly visible and emotive problem. It's something that the public engage with. And all of us as the public use plastic on a daily basis. So actually, a small shift by many could achieve quite a big movement forwards, in my view, as we move, hopefully, towards less wasteful, more sustainable behaviour, but as a consequence of which produces less waste. So I'm going to stop there and say thank you very much for listening. We've got a bit of time for questions. If you want to find out more, just Google the International Marine Litter Research Unit and you'll find out more about the various papers there. I'm happy to email you things if there's something else of interest. So thanks very much. Thank you for having me.
Richard, and sorry that you've all been conned into listening to I'm sure Richard will be happy to take some questions.
Yeah, brilliant talk. Really enjoyed that. You talked about the deep sea, and there's lots of plastic in the deep sea from your studies there. Obviously, one thing about the deep sea is that it's often very cold, and the turnover time for populations can be very long. So is it that the litter there, or the debris there, is a time bomb waiting to go off, or is it actually going to be sort of broken up over a much shorter time scale?
I don't think we know, Dave, is the answer to that. I mean, when we first started working on this issue, one of the first grants I applied for was to look at patterns in space, at spatial distributions, where the litter was, because I felt that if we did that, we could then understand what organisms might be affected, because we knew where it was accumulating. Because if you think of a risk assessment, it's about probability of encounter. But the reviewers' comments came back, oh, we don't want to know about this. I mean, only anybody's going to care if it's harmful. You're going to need to know, show if it's harmful. So then we went off down that track, and of course now there is evidence of harm, but we're only going to fully understand what the risk is if we know about the probability of encounter. So we're going to need both at the end of the day. And I don't know whether those original NERT reviewers were right, that we had to look at harm first. What the order should be, I felt the appropriate place was to look at distribution. But, you know, so we're going to need to know more about, in essence, the answer to we need to know more about where the hotspots are. I'm thinking the deep sea could be one of them, but we don't really know that much about it yet.
Richard, one of the things I became conscious of years ago doing some Newston netting in oceanic water was the amount of polystyrene, small beads, feedstock sort of stuff. Is that something that we should be particularly concerned about? Because it's so close to the sea surface?
If it was polystyrene, it probably wasn't feedstock. It was probably buoyancy that had broken down. You know, you get a polystyrene tile and it'll break into balls quite quickly. But there are balls that are used as feedstock. These are these things called mermaids' tears or nurdles, but they're typically polyethylene. They're not often polystyrene, but they're melted down to make the products that we use. And some of them are big bits the size of a lentil. Others are actually quite small powders that are used. And spillage of those is certainly important. But I think the industry's done a lot over the last decade to help to reduce that leakage from their own systems. I'm not saying that it doesn't happen. You know, if a container's lost overboard in a storm, it can happen. But I think that there have certainly been attempts by industry to try to reduce that leakage. It seems a more immediately manageable problem, let's say, than this very diffuse leakage of waste from many different systems. But it's definitely part of the picture, and those bits are, of course, readily ingestible.
Your slide on desorption of pots suggested that they aren't readily desorbed in seawater.
Yes.
Do you have any handle on what the half-times are, some of these compounds?
I could certainly send you the paper later on. I mean, the thing to recognise there is it's an equilibrium. So if you've got water that's contaminated, they'll go on. If the particle then drifts to a place that's a lower level of contamination in the surrounding water, it's going to come off. So that equilibrium is going to be driven by the concentration in the surrounding water and what's on the plastics. And one of the things we looked at was modelling from plastic particle flowing through a river through estuarine conditions, which are typically fairly heavily contaminated in many places, and then maybe flowing out to the open ocean. And how quickly would that burden of chemicals be given up? And we kind of reached the conclusion that, yeah, if you were a fish feeding near the mouth of an estuary and you were getting a particle within 1 or 2 days of it leaving the contaminated estuary, you might get an elevated hit compared to eating a piece of plastic that had come from further out in the ocean. But after, you know, days to a week or so, most of those contaminants were leaving. But it also depends how deep in the plastic the contaminant is. It's the porosity of the plastic and how long it's been in environment A compared to environment B. So it's not a simple answer to that, but it is a kind of equilibrium. It is an equilibrium that's going to be driven ultimately by the concentration in the plastic and that in the surrounding water that's going on or coming off. I don't know if that answers a little bit, but I can certainly send you the paper that would go into more details of the rate constants.
But you're suggesting that it is totally reversible. Eventually it will all come back out of the plastic.
I don't think we really know the answer to that, because a lot of the laboratory studies have been over quite short periods of absorption of acquiring the chemical and then the subsequent release. But if you think about a plastic acquiring chemical over a much longer period in the environment, then we don't really have answers to that. What has surprised me when I've looked at electron microscope pictures of the surface of some of these plastics is they're incredibly complex. There are caverns that disappear into them, like it's a kind of a limestone region that you imagine caves going for miles. If you look, if you're looking at it, and so there's a potential for retention in these particles. But the other issue I touched on was that of the additives, which, if they're incorporated right through to the centre of the plastic item, they may take considerably longer to come out than something that's kind of absorbed from the outside in and then coming back out again.
Finally, the metals behave the same as pots.
Yeah, we published on metals, and there's a paper on the website, and there's certainly similarities. It varies from metal to metal, but yeah, they'll behave in a similar way.
So I'll go one, and then I'll take that one.
You've obviously been working on this for a while, and most people here, I imagine, recycle and get a bit frustrated with the amount of plastics that you can't recycle, and you've just told us coloured ones are causing all sorts of problems. What sort of buy-in or interest or commitment are you getting from industry? Are you engaging with industry, and are they working on developments?
So, I've been engaging with industry for over a decade, and they, I'm pleased by it to a large extent that, certainly if you think of the plastic trade organisations, Plastic Europe, for example, they don't want the plastic story to be one about contamination. They want it to be one about the products that bring societal benefits. So, it brings them no advantage. This isn't a kind of unavoidable consequence of an industrial process, that there's this emission of a gas or something. So it's in their own interest to try to clean up the act. The problem comes in who's actually responsible along the supply chain, because at the one hand you've got the oil being taken and turned into plastic, and then that's maybe going into these little beads that you talked about, and that's going further on, and that's being turned into maybe a product, but maybe not still quite at that end stage. And then you've got a large retailer or maybe a warehouse, and then you've got the consumer, and they tend to point the fingers at each other and say, the consumer demands green bottles. And I'm thinking, do you? Probably not. But somewhere, somebody's convinced there's that demand. And so there's always this elephant that's kind of in the room but not in the room in terms of trying to get that engagement. It needs to involve the whole supply chain, I think, and when I say the supply chain, I'd actually include the waste managers as well, because they're the best ones to identify the problems. You're doing your best to put your stuff in the wheelie bin or whatever, but if it's not going anywhere as a consequence, that's a waste of time. But when it equally well could do, perhaps be better designed. So I am engaged, but it's trying to bring quite a complex supply chain together. That's actually one of the challenges, I would say.
You didn't really talk about physical transport processes and sources and so on. But those things are very relevant, very important to individuals. I snorkel and dive a lot in the Mediterranean, and depending on whether you have a few days of downwelling winds or not, the difference in a dive site can be huge.
Yes.
On one occasion you can have a disaster of plastic bags and bottles, plastic bottles. Another day it can be beautiful.
Yes.
Similarly, if you, say, walk Bristol Avon, up estuary of the Weir towards Bath, what you see is the trees that are overhanging the river are basically Christmas trees of plastic bags.
Exactly.
So the sources and the transport paths must be important.
Oh, absolutely.
But so maybe there are other studies going on.
Oh yes, I mean, there's work on that. I mean, I hinted at some of it when we looked at the modelling of the global distribution at the sea surface, and if you try to match that with empirical data where there's long-term data along transects, you see some correlation between the two. So we know that wind and tide are going to be really important, the upgoing and downwind, but we still don't, we can sort of paint a global picture, and in a river where it's a linear system, it's a little bit easier to get a finer scale of resolution. But I think the problem is that this analogy might not work for some of you, but it's a bit like if we're rocky shore ecologists, which is where I kind of came from, and we want to do a study on rock pool fish and go and count them, but we haven't yet realised what it is that defines or makes a rock pool. So we're sort of looking for them in sandy beaches, and they aren't there, and we're looking for them on dry rock, and they aren't there. We don't fully those processes are absolutely fundamental. We don't yet understand well enough how they drive the patterns of distribution, because if we did, that would actually help our data collection when we're looking at monitoring and long-term trends. That's part of why the picture is so noisy, this variability, is we don't actually quite understand where and when to count this stuff. So what you're saying is absolutely right. Just before I came down here, I actually submitted a letter of support for a postdoctoral fellow that wants to work on some of those physical properties at quite a fine scale of resolution. So fingers crossed for it.
Particularly, I imagine that estuaries could be very important in all of this.
Absolutely. Well, rivers, I would say, are really important as an input to the ocean. You look at a river and you might not think it's so contaminated, but you have to realise that it's continually flowing, and you've got to tot up the quantities that are passing via between A and B over a year, over 10 years. And I think rivers are really important. The other thing, the reason that they're really important is they're a way that when you talk about marine litter and you talk about it hundreds of kilometres inland, people think it's a problem that's just to do with those people that live by the sea. It's generated at the coast, it's on the coast, and actually, even hundreds of miles from the coastline, you can be a source of marine litter via rivers, so I completely agree.
Okay, we're running very short, so if they can be very quick questions and very...
I'll try and quick answer, yes, sorry, that's my fault, yeah.
Right.
The short cycle of buying it in the supermarket, use it, chuck it in the bin, goes to the council, gets recycled. Sounds like it's relatively easily manageable and it's using stuff that's easily used. Long cycle stuff, where you've got mixtures and it's been in the sea and it's had all sorts of stuff done to it, is that much more difficult in order of magnitude, or is it just a bit more difficult to recycle?
I think it's where there's high value. So, I just bought a new telephone from BT and they sent me with it a bag to return the old one because there's high value metals and all sorts of things in there that they want back. I'm most worried about the single use stuff because it's our main use and it's so rapidly accumulating as waste. But of course we need fixes to the long-term durable goods. We've been good at doing that with parts from cars for a long time, and we don't want to stop doing that, but it's this single-use stuff that's ending up in the sea. So I think you've got to start somewhere. I don't want to stop the longer-term applications and recycling there, but I think it's the single-use things where I think we could be doing a lot more to make progress more quickly.
Okay, I'm going to stop now. Because we need to, those of you who are going to come to the AGM, make your way over to the